You can start.
Okay, let me share the screen. Can you see my screen?
Yes.
Okay. So hello everyone. This is Sunan. I'm from the Hong Kong University of Science and Technology, and I'm very honored to present our work, GSCo, which titled towards generalizable AI in medicine via generalist-specialist collaboration. So the problem we want to address is trade-off in medical AI. Medical is inherently multimodal. It has a lot of modalities. So we want to build a unified model that can handle different modalities and different tasks. We collect a lot of data, but in practice, we may prefer the specialist model. For example, if we want to address specific tasks, for example, classifying a single type of pathology or identifying some specific condition in a checks X-ray. So we may just train a lightweight resonance model on this classification task. Because the specialist model always have higher precision, but it comes at the cost of flexibility. If we just train a model on a specific task, it will have limited generalized capability. So on the other hand, we will have generalist models, for example, something like GPT-4. It can handle diverse tasks, but for a single specific task, it may not be the best one. So the problem we want to solve is, can we design such a unified framework that can reconcile these two paradigms, the specialist and the generalist? So how do we achieve such a collaboration between the specialist and the generalist? A straightforward A straightforward method is we can build an agentic framework. There are some recent works about the multimodal agentic AI in medicine. As you can see, most of them formulate the paradigm into delegation. For example, when the query comes in, the large language model will allocate the task to the agents. Then they will summarize the results from the agent and the output to the user. So this paradigm, just like a router, the generalist foundation model, the primary job of generalist foundation model is to delegate. It receives query, analyzes it, and selects the most appropriate specialist tool from his library, and then just summarize and output the results from the specialist model. So we think that we have already if we have already have some powerful generalist foundation model in medicine, we should use the generalist model as a final decision maker. So the generalist model is not just a router or delegator. It should be make the final decision based on both its inherent knowledge as well as the reference from the specialist model. So in this work, we want to build such a collaboration. We named it GSCo. So this is a generalist-specialist collaboration. We want to use the domain-specific knowledge of specialist model as well as the generalized capability of the generalist foundation model. So our framework can be divided into two stages. The first stage is the construction of the generalist and the specialist. The second stage is the collaborative inference on the downstream task. So in the first stage, we curate a large-scale dataset to train our generalist foundation model. Then we train a lot of very lightweight specialist model on some specific tasks. So during the inferencing, we propose a mixture of expert diagnosis and as well as retrieval augmented diagnosis with two core mechanisms to facilitate the collaboration between the generalist foundation model and the specialist. So first is the data curation. About the data curation, we incorporate more than 2 million image text pairs into our training data to build our generalist foundation model, and we cover 5 types of tasks. For example, some classical tasks like classification, medical report generation, and VQA. Meanwhile, we also propose a diagnosis-guided bootstrapping method to augment our training data. I will talk about it later in detail. So we also create a very large-scale benchmark to evaluate the model's performance comprehensively. Our benchmark consists covering medical report generation, medical image classification, and the visual question answering. So let me have a deeper look on the diagnosis guided bootstrapping. We found that current the generalist foundation model, such as GPT or some open source work such as QueenVL or InterVL, they just fail to do the well medical image analysis because they cannot correlate the disease with the image. For example, in this subfigure, as you can see, it do know the knowledge about the colitis, but it cannot correlate this disease colitis with the image. If we just input this image, it will get a wrong diagnosis. So the problem we found is that the generalist model may have the generalist model in natural domain may have some difficulty in correlate the concept with specific visual evidence in the image. So we want to so our method want to use the diagnosis of the image to bootstrap our training data. We want to use this diagnosis information as a guidance to help the model to analyze the image and generate more comprehensive reports. So in the data curation, we just based on the classification data set, which have the image and its paired ground truth diagnosis label. So we just input the label as well as the image into the generalist foundation model, and we ask him to generate some more comprehensive report, more than just a label. So we believe this can help model to building the it will teach the generalist foundation model how to visually reason and articulate diagnosis to correlate the concept with some specific visual evidence to enhance the inherent diagnosis capability of the model. So this is this is the strategy in our data curation. So here is our the second stage about the collaborative inference. So we propose a mixture of expert diagnosis as well as retrieval augmented diagnosis. We want to make the generalist foundation model is not just a simple router. We want to make him as the decision maker to make the final decision based on both inherent knowledge as well as the reference. So let me look at it step by step. So in the first step, it is a mixture of expert diagnosis. we just input the test image into a suite of specialist models, and this specialist models will give their predictions separately. In the second stage, it's called retrieval augmented diagnosis. We just input the test image into the best one of specialist model. We want to use this model as the retriever to retrieve the similar cases in our database. It is just very like a clinician review in a patient database. So we retrieve the most similar cases in the our database and retrieve their meta information. So in the third stage, it's called collaborative information. We just input the test image, the task instruction, as well as reference information provided by both mixture of expert diagnosis as well as visual augmented into our generalist foundation model. So we ask him to make the final decision based on all of this information. So through this way, we can achieve a more comprehensive collaboration between the generalist state foundation model and the specialist foundation model instead of just something like a router paradigm. You just allocate the task and output the result from the specialist. We want to achieve real collaboration between the generalist model and the specialist. So here we first test the overall performance of our generalist foundation model, and it achieves a better performance than previous work. So it is a strong foundation of our collaboration. Then we do some ablation study on our framework. We demonstrate the results demonstrate that our the proposed strategy MOED and IED can work effectively. We also compare the whole framework with the recent state-of-art medical image analysis foundation model BioMed-GPT. We also achieve better performance on several medical image analysis tasks. Okay, here is two qualitative examples of our collaboration. So the first, the top one is example of MOED. As you can see, different the specialist teams do have very different predictions. Half of them predicted positive and another half predicted negative. If we just use some naive ensemble baseline, for example, we just use the voting, it will fall in this situation because half of them are positive, half of them are negative. But if we provide this information into the generalist foundation model, it will not only considering the results from the specialist model, it will also analyze the image itself and give the final decision. The bottom one is shows the example of retrieval augmented diagnosis. The specialist model acts as a specialized retrieval. It will query the database and retrieve some very similar cases in the database, and the retrieved cases will act as the guidance for the generalist foundation model to make the final decision. As we can see, both of this strategy can effectively provide a reference to the generalist foundation model. We also compare our framework with the agentic frameworks. For example, the MMed agent. We found that we can achieve better performance on multiple medical image analysis tasks. In this work, in this experiment, we to test both our foundation model and the generalist foundation model in MAD agent within both framework, which means we put our generalist foundation model into their framework and see our from performance. We also put the generalist foundation model into our framework to see that the performance of their generalist foundation model. So the first conclusion is that we found that even within their framework, MADR can achieve better performance, which demonstrates the superior capability of our generalist foundation model. Another conclusion is that, as you can see, our framework can achieve better performance than MAD agent on specific task. This is because MAD agent use biomed clip as the classifier, so it just input the image into the biomed clip and summarize its the prediction of biomed clip and output. So the first thing is that the inherent capability of biomed clip is limited, and the second is that they just output the result without considering its inherently knowledge, so it achieves inferior performance. In contrast, GSCo will utilize both the knowledge from the generalist as well as the domain-specific knowledge from the specialist. So we also conduct an interesting experiment about GSCo vs monolithic baselines, which means we have trained a generalist foundation model. What about the performance if we just continue to fine-tune this generalist foundation model on specific tasks? Can we achieve better performance instead of design a complicated framework, relatively complicated framework like GSCo? Actually, as you can see in two of the tasks, fine-tuning such large-scale model on a specific task, you will get better performance. But the significance is not very higher. And as you can see, if we want to adapt in such a large-scale model, it will be very costly, much higher than the cost of building a GSCo framework. So this experiment demonstrated that GSCo is not only an effective framework, it is also an efficient and scalable paradigm. It will achieve better performance with relatively much lower cost. So we also do some robustness analysis, so to test what happens if the reference is not correct. So the first experiment in the left one, as you can see, we compare our model with our baseline model InternVL. So we provide them both of them with reference of varying error rate, which means in this point we provide the reference which are all correct, and in this one we will provide in this point we will provide the model with all erroneous reference. So as you can see, compared with InternVL, our model is more robustness. You may see that you may note that in this data set, the InternVL it just output the reference without thinking. So it's just very adhere to the error portion of our provided information. And in the right figure, we test the situation that the specialists have some systematic bias, which means we provide the information belong to a single classes. For example, this is a pneumonia detection dataset. We set all reference to the normal. We want to test in this extreme situation, what is the performance of our foundation model. As you can see, uh, even with all of the reference are set to the normal, our model can still recognize and detect the pneumonia situation into the image. So we found that our model can have some resilience to the biased guidance. We also want to test our model in conflict scenarios. We do the experiments like this. So first we will get the initial and the independent diagnosis of a generalist foundation model. We just also this is a pneumonia detection task. So maybe for example, Matter's first initial diagnosis is normal. Then we provide pneumonia as the reference. So this is a conflict scenario. We want to test the model's robustness in this conflict scenario. Can he still get the correct answer finally? So as you can see, even with this conflict scenario, our model will also achieve very robust results in both data set. As you can see, in the if the results are initially correct, most of them are still correct, even with the conflicting and erroneous result. And if the initial prediction is incorrect, some of them are correct. Some of them are correct. Most of them are correct during the collaboration between the generalist and specialist. So we will get the final, most final decision very robust and impressive. So we want to have a deeper look into how this work. We want to see the reference provided by specialist is a gap filling or it is a collaborative reasoning. Concretely, we divide all of the sample into 6 cases. So the first case is that both model predict, which means our collaborative framework as well as standalone generalist model. So if both of them are correct, it's perfect. But if there are some if there are some errors in GSCo or MedDoctor, we will see the reason. So the second scenario is that GSCo is correct, but the baseline is erroneous. The third situation is that GSCo is correct, but the guidance is not very helpful, which means the guidance maybe have some erroneous information. And the last 3 cases is the failure cases. We divide them into the failure but correct guidance, the failure with the incorrect guidance, and shared failure. We can see in this distribution, if we have correct guidance, there is no failure in this table, which means we can always leverage this correct guidance. But if, of course, if the guidance have some failure, some of them may derive erroneous prediction finally. So this experiment demonstrates that our framework can both utilize gap filling as well as synergetic reasoning to achieve a more robustness and better performance. Of course, our framework achieves some promising results. There are still some limitations. So first is that our model currently only support 2D images. We want to incorporate more modalities into our model as well, because there are some 3D and time series information in the medical vision is also very important. And second, we want to improve our retrieval strategy because reliable reference play an important role in the final decision. The higher accuracy the reference, we will have higher accuracy in our final decision. So we want to use a more precise multimodal retrieval strategy to improve the reliability of our retrieved information. We also want to explore more advanced collaboration paradigm between the specialist model and the generalist foundation model. Maybe there are more complex interaction between them. Then we will try to test our framework in the clinical scenarios to see can our model help the doctor to make the final decision. So here is our conclusion. So in this work, we build a leading generalist foundation model tailored for medicine. It is a multimodal. It can handle diverse medical modalities as well as medical tasks. Then we propose a collaborative framework called GSCo, which leverage both the generalized capability of generalist foundation model as well as the domain-specific knowledge of specialist model to achieve the generalist-specialist collaboration. Okay, and we propose two effective and efficient strategy mix of expert diagnosis as well as retrieval augmented diagnosis to facilitate such collaboration. Okay, I think that's all for my presentation, and thanks for your attending and welcome questions.
Thank you for the talk. I can start with the questions and then you can make other people go. But for can you go to slide 10? When people usually say specialist models, they mean models trained for different tasks. So you can have one that does report generation, one that does segmentation. But in your case, it's different architectures, right? But it's all they're all trained for the same tasks, but you just have different architectures like VGG, ResNet, EfficientNet, and then all of these other models, and they all make the same, or they all perform the same inference task, and then you have multiple predictions, and then use that for the foundation model, for the generalist multi-model LLM to incorporate this, right? Am I correct in this, in describing this?
Yes, we train a suite of specialist model on the same specific task. So all of them do classification on this task. Yeah.
Then what's the point of including all of these? If you have, let's say, 3 models that are top 3 performing models from the perspective of this task, why don't you just use those? Why do you have all the 10 different models? What's the motivation behind that?
Yeah, actually, we also do additional experiment about the ablation study of the number of specialists. We found that if we only have one specialist model, it will it may tend to get erroneous prediction. We want to use the paradigm of ensemble. So we tested the different number of specialists and found that 10 specialists have better performance. If we have lower number of specialists, for example, 3 specialist model or 5 specialist model, it may also achieve some compatible performance, but the overall performance is lower than 10 specialist model. And if we use more specialist model, on the one hand, it will have a higher cost. On the other hand, it will have more discrepancy between the specialist model, which will make the generative foundation model confused. So this is a balance about this is a trade-off that you which the number you should choose in the number of specialists.
Okay, but so instead of, because my other question is like, why do you need VGG and AlexNet on these older models, ResNet 18? Because one other thing you can do is, let's say the number of specialist models matters. You can just have a model in architecture, say like Dino, VITB, and just fine tune 10 of those with different seeds. They just start with different seeds, and then you're going to end up with 10 different models that might generate different predictions, but they're all better. They should be better from an architecture point of view than using VGG and AlexNet and ResNet 18. All right?
Yes, we want to build our the suite of our specialist model become more heterogeneous. So on the one hand, I see in some recent papers, for example, the model like ResNet or VGG, they still have some competitive performance. It may not very out of it. It still have some competing performance. So I think we can use this model. And on the other hand, we want to make our model, the structure and the design of our specialist model more diverse. So it will complement each other to achieve a better performance.
Okay. Okay, and then can you go to slide 13? Can you go to the next one?
Okay.
Okay. Okay, makes sense. Okay, I don't have other questions.
Hi, Sunan. Hi, Mohammed.
Oh, hi, Louis.
A great talk. Thanks for the sharing. When I see your sharing, it makes me think of Google's Gemma, which is released this year and is also supposed to be a generalist of LM and supposed to
Yes.
have a very good results. Have you compared with that model later on? I know your work is definitely earlier than Gemma.
Yeah, MetaGamma is very competitive. Actually, we compared it in our next version of MedDocs generalist foundation model, MedV2. So maybe we will release our model early next month.
So what is the next plan for you to scale GSCo up? By scaling up, I mean, do you plan to get more data, or are you scaling up in the dimension of specialist?
So the first direction I think is is that we want to support more modalities. In the next version of our generalist foundation model, we will support 3D modalities such as CT and MRI. We will also support time series data as well as the video data. So we want to use our model to handle more modalities than the current generalist foundation model. So the second direction, I think, is it is a more complex collaboration paradigms. It may be involve some chain of thoughts and reasoning during the inference to improve the collaboration between the generalist and the specialist.
I have a follow-up question. So when you say
Yeah.
chain of thoughts, do you mean the chain of thoughts of one task or multiple tasks that combines to complete one clinical, one complete clinical trajectory? Like
Yeah, I think
for you to diagnose one patient, you have to go through a lot of different data, not just one.
yeah, actually, yeah, we we want to explore this. We want to use our framework to can handle different modality simultaneously. So we can just not only analyze a single modality data, we can analyze all of as more data as we can to give the final decision of the patient. Yeah, we
Yeah,
do want
please
to
go on.
explore it.
Sounds pretty impressive. And by the way, Mohammed here has a paper called Rex Grounding CT, which I hope if you find it useful and helpful, please consider use this data set as well.
Okay. Yeah, I actually I just download Rex. I think I just downloaded this dataset. Yeah.
Nice. Okay. Thank you very much for sharing and for the answers.
Yeah.
Great work.
Thanks for your invitation.
I have a question as well. So the foundation model here is plays the role of not just listening to the specialist. It also has its own decision making, and it uses the specialist as guidance, right? Because when you first
Yes.
proposed this framework, when you first proposed this, or when you're going through the first couple of slides, I thought that the generalist model will always just follow whatever the specialists say. Because I think LLMs would have a tendency to just follow like the previous the whatever described in the previous tokens or text. So how did you prompt this so that it's not completely relying on the specialist? Like, what was the prompt that you were using so that
Yeah, we just used prompt like this. Actually, we only say this is a reference. We do not say this is you must you must follow this guidance. This is just a reference, and because of the diverse of the reference, it may be not easily to just use leverage a single reference. So it will considering diverse reference as well as inherent capability. So of course we do some prompt design in this work.
Because you also showed an example where all of the experts say no pneumonia, but the actual case has pneumonia, and then the model correctly gets that it's pneumonia, right? I remember that was
Yes. So this is the reference instead of we only call this reference.
yeah.
So yeah, I think the model can have some robustness to the reference. As you can see, even without the specialist guidance, our generative foundation models has already have some competitive performance on this pneumonia detection task. So guidance will achieve better performance, but without guidance, we can also achieve some satisfying performance. Yeah.
Okay. One just a quick question also that I just thought of. instead of feeding the classification label to the model, you're using Lava, right, as an architecture for the mid DR, right?
Yeah, something like Llama. Actually, we build our model based on interview, which is the structure in interview is very similar to Lava.
Okay, but I'm saying like it can take in multiple different image embeddings, then be projected to the same space as LLM. Why if you feed in the embeddings of the last layer from the specialist models instead of just a classification? Or actually, that's going to be very yeah.
You mean during the retrieval? Yeah, we do explore more complex retrieval strategies, but previously we do some lot of exploration, but we found that the single embedding retrieval is the most effective one. So we just use the specialist model to retrieve the data.
Okay, makes sense. Okay, if there's no more other questions, we can stop here. Thank you, Sunan, so much for joining us today.
Okay.
It was a very interesting paper. And congratulations, I've heard this paper was accepted in just recently in Nature Biomedical Engineering, right?
Yes.
So
Thanks for your invitation.
Congratulations and best of luck in your PhD.
Yeah, thank you.
Right.
Bye-bye.
Thanks everyone, and see you guys in the next week in the next episode. Right, bye.